Okay, in this screencast we want to talk about solving eigenvalue problems. To solve eigenvalue problems, we again use the linear algebra routines from SciPy. So we're going to again look at the documentation. We've seen this before. We've gone through a bit of it. In this case, we're going to be interested in a few things. We're going to see inverse, which is going to be useful for us, and det for calculating determinants. And those will be useful things, and there'll be a few other things that we pick up along the way. But the things of main interest are, well, we want to solve eigenvalue problems, so there's routines for doing this. The main routine for doing this is eig. Okay, as it says, this finds eigenvalues and eigenvectors of a square matrix. Okay. If we're only interested in the eigenvalues, sometimes we don't need the eigenvectors. Then there's a specialized routine eigenvalues, which just gets the eigenvalues. This requires less work, so it can be done more quickly. And so again, if we only need the eigenvalues, it makes sense to just use that specialized routine. Okay, so there's these two routines which basically do the hard work for us. There's two other sets of routines, just specialized versions of this, or useful in other circumstances. So eig_h and eigenvalues_h. Okay, these are if we have a symmetric matrix, or if we're dealing with complex matrices, a Hermitian one. So we can use those in those special cases, okay, and we'll see examples of that. And then there's banded versions of these, okay, much like we saw there was solve banded. If we have a banded matrix, like a tridiagonal matrix, then it's useful to again use these specialized routines. And we'll use eigbanded in the lab this week. Okay. So that's mostly what we want to talk about in this screencast. So let's start with a matrix. So let's pick some matrix, call it A. This matrix we've seen before. This is the matrix that we used when we were solving our system of equations last week. And so we know things about this. We know, for example, that the system of equation the system of equations from which we get this matrix does have a unique solution. If we calculate the determinant of this, we see that the determinant is non-zero. Okay. And that means that this is not a singular matrix. And for a non-singular matrix, we know there's a unique solution. Okay, so that confirms that. Okay. However, here we're interested in eigenvalues and eigenvectors for this matrix, and that's what eig does for us. So let's look and see what eig does. Okay. Well, it has a lot of options. There's only one that's required, A. Okay, this A is a square matrix, m by m. It can be complex or real. And this is the thing for which we want to calculate the eigenvalues and eigenvectors. Okay. All the rest of this stuff is extra things that we don't need to worry too much about. If you've studied eigenvalues and eigenvectors before, you might have talked about the difference between right and left eigenvectors. Okay. By default, we calculate the right eigenvectors. That's the equation we had written down before. The matrix A times a vector V is equal to lambda V. Okay. We're not going to worry about the difference between these. The default is what we want, so we'll go with that. There's also these overwrite options, like we saw last time for the solve routines. We can also feed in another matrix B, okay, the right-hand side matrix, to solve a, quote, generalized eigenvalue problem. Okay. We might talk about that more in class on Wednesday as an example. This is useful, for example, in finding normal modes of a system of oscillators, which is something that should be studied in classical mechanics. So again, we might talk about that. But again, for our purposes, we don't need to worry about that. Really, all we need to feed it is a matrix, and it's going to return W. Well, it calls it W. We call it lambda. I'm going to continue to call it lambda, which is the matrix of eigenvalues. Okay? And depending on which one we pick, okay, we're going to be dealing with right eigenvectors, so what they call VR here, what we called in class B, is this m by m matrix that contains the eigenvectors for each of the eigenvalues. Okay. Okay, so let's look at this for our matrix A, and here we go. Well, the first thing that we notice is this looks kind of surprising, or there's lots of strange looking things here. Okay. So again, the first thing that's returned is an array of the eigenvalues. Okay, so these are the eigenvalues. We have a 3 by 3 matrix, so there's 3 eigenvalues. Okay, and here's the eigenvectors in another matrix. Okay, so since this is kind of messy, let's store these. As we said, I typically call the eigenvalues lambda. Lambda is a keyword in Python, so I don't typically overwrite it, although I suppose we could. So I just call it lam. It's also less to type. And b is what we had called this matrix in class. Okay. So the first thing that we notice is that these lambdas, these eigenvalues, look kind of strange. This is a complex number, or this is how Python represents complex numbers. Okay. It uses j. Well, I typically use I to mean the square root of -1. Here they use j is equal to the square root of -1. And so I guess that's standard, for example, in electrical engineering. But anyway, that's a complex number. So in other words, 1j is the complex number that I would typically just call I. If we take 1j squared, we see that that's -1 plus 0j, meaning there's no imaginary component. This also allows us to calculate the famous result that e to the I pi is equal to -1. Or if we just look at the real part of that, e to the I pi is equal to -1. Okay. So that's complex numbers. That's really all that we're going to say about them here. A real matrix can have, or does in many cases, have complex eigenvalues. Even so, we've done the eigenvalue decomposition. The eigenvectors are also complex. Okay? But that's not a problem. We can calculate the inverse of this matrix using inv. Okay, this is B inverse. We can verify that this is the inverse because B inverse times B should equal the identity. Okay. Well, that is the identity. Again, it's a little messy because there's complex parts in here, but you'll notice that all of these things are of order 10 to the minus 17, or 16 or 17, except along the diagonal. We can look at that a little more clearly by taking the absolute value of it. This is the magnitude of it. Okay. And furthermore, we can subtract this off from the identity. Now, the identity is the diagonal matrix with ones along the diagonals. That can be constructed in a number of ways. In fact, an easy way to construct it is it's already done for us. Okay. I, spelled in a funny way, is with ones along the diagonal and zeros everywhere. This can actually do more complicated cases. For our purposes, we want a 3 by 3 identity matrix. There it is. And so if we take this minus the identity, whoops, okay, we see that yes, this is 0. Okay, again, up to the usual numerical precision. So this is the inverse, even though it's a complex matrix. And we can also calculate okay, B inverse AB. We said that this should diagonalize the matrix and that along the diagonals should be the eigenvalues. So we can verify that that's true. Well, okay, that's really hard to read. Okay, it's hard to see that yes, on the off diagonals really are approximately 0, and along the diagonals really are the eigenvalues. Okay. Again, what this is supposed to be is a diagonal matrix with the eigenvalues along the diagonal. Well, how can I construct such a matrix? Well, once again, there's something that does it for us, diag. Okay? Diag either extracts the diagonal if we feed it a matrix, or it constructs a diagonal matrix if we feed it just a one-dimensional array. So in other words, if we feed it the eigenvalues, what do you know? It constructs a diagonal matrix with the eigenvalues along the diagonal. And so this means I can do a similar thing. I can subtract off, whoops, let's try to get that right, the diagonal matrix made of the eigenvalues. Okay. And we see that, yes, that really is zeros. In fact, let's calculate the absolute value to see that it really is small. We can even find the maximum value in that and see that the maximum value is 10 to the minus 14. So yes, we did a really good job of diagonalizing this matrix. Okay. Okay, so again, that's the basics. Run through somewhat quickly, but you can go through that again, okay, of how we calculate these things and verify that we've gotten things right. Okay. Well, let's look at another matrix. Let's look at the matrix that we considered in class. Actually, this isn't the one that we considered in class. Double check this. Yeah, that's right. Okay, so this is the one that we considered in class. There we go. So in class, when we worked through an example, whoops, we considered this matrix. Okay. So let's again calculate the eigenvalues and eigenvectors for this matrix. And here we go. We get some answer. Okay. Again, the answer can be complex, so it stores it as a complex number even when these turn out to be real, at least for the eigenvalues. For the eigenvectors are also real. Okay, and these are consistent, or in fact identical, to the ones we found in class up to signs, as we talked about. I can always multiply any one of these by a sign, and that doesn't, and it's still an eigenvector. Okay. Now this A that we had done in class turns out to have real eigenvalues. In fact, we knew that it was going to have real eigenvalues because this is a symmetric matrix. We call that a symmetric matrix means that A and A transpose, okay, are the same, or in other words, A minus A transpose better equals 0. Okay. For a symmetric matrix, it turns out, or you can prove, that the eigenvalues are always real. And as we saw, we can use a specialized routine for this, eigen. So eigen looks very similar to eig, although it's got a few extra options that, again, we're not really going to deal with. One important thing to notice is since we're dealing with a symmetric matrix, we don't really have to store the full matrix. We could only store the lower triangular part or the upper triangular part. And in fact, the routine only uses that part of the matrix. By default, it uses the lower part. We can instead have it use the upper part. Since we've specified the full matrix, both the lower and upper, it doesn't matter what we use. But in principle, the upper could contain junk, and we could still use this routine if we just use the lower part. Again, the defaults are set fine, so all we really need to do is feed it our matrix A, which is assumed to be symmetric. By assumed to be symmetric means it's only going to use part of the matrix. It's not going to check for us. Okay? So we could feed a non-symmetric matrix to this, and it will happily pretend like it's symmetric. So again, we have to be careful when we do these things. Okay? So let me rerun the old one, just so we can see for comparison. If we run eigen, notice it can construct real eigenvalues because it knows that the eigenvalues are real. Okay. Also notice it gives us the answer in a different order. Okay. The order doesn't matter. Here we didn't really comment that it put them in a different order than we talked about in class. Okay, whereas eigen has ordered them, in this case, in ascending order. Okay. It doesn't matter. Okay. Notice that the structure of this matrix must also change to be consistent with that. This first eigenvector here, 0.8, 0, 0.5, is the eigenvector associated with the eigenvalue 6. Since 6 now is the last one here, notice that this now appears as the last column instead of the first column. Okay. Also notice if we look at the eigenvector associated with the eigenvalue 2, which appears here in this matrix, it appears here in our other matrix, and these differ by a sign. Again, that doesn't matter. The sign is unimportant. Both of these are eigenvectors, and the algorithm, for whatever reason, given how it was constructed in the order that it does the calculations, decided to make it positive here and negative here. Similarly for the eigenvector associated with the eigenvalue 3. Okay, these again differ by a sign. Again, that's arbitrary and it doesn't matter. Okay, so the point is that we can get different orderings, okay, and different signs, even between the two algorithms acting on the same matrix. Again, these are all still valid, and there's no problems or no issues here. Okay. We can again store these in our matrices. Now we also said for a symmetric matrix, okay, that it turns out that this matrix of eigenvectors is orthogonal. We call that orthogonal meant that B transpose is equal to B inverse. Okay. In other words, if we take B transpose times B, this should be the identity, because B transpose is just B inverse. And what do you know it is? Okay, we could also subtract I off of this, but this is easy enough to read that clearly this is the identity. Okay. That also means that when we did this comparison, we can now do this comparison more easily. Now it's B transpose AB that will give us the diagonal. Okay, and we see that yes, that in fact is true. Okay, so it gives us the diagonalizes the matrix with the eigenvalues along the diagonal. Okay, or if we prefer, we can look at that and read them off just as easily. Okay. Okay, so again, that's the basics. Whoops. There's one other case that we will look at. Okay, so here's one other matrix that we could play with. This is also a symmetric matrix. Okay, that should be clear. And so I can also use eigh to calculate the eigenvalues for this. Okay. In this case, we have degenerate eigenvalues. Okay, that means that two of the eigenvalues are the same. Okay. There's nothing wrong with that. Okay. This B matrix is still matrix of eigenvectors. Okay, here's the three eigenvectors. Okay. It's still true that this is an orthogonal matrix, so B transpose B is the identity. Okay. It's still true that it diagonalizes the matrix, okay, with 1, 1, and 6 along the diagonal exactly as it should do. Okay. The one difference here is that this reports some eigenvalues. Okay. Reports some eigenvalues and some eigenvectors. Okay. For degenerate eigenvalues, okay, so these two vectors are not unique. Okay. To say this a bit more formally, for those of you who have seen this before, what this means is that this subspace spanned by these vectors is only defined up to a rotation. So I can rotate the vectors in this subspace and they will still be eigenvectors. To say that in words that perhaps you'll understand, two vectors define a plane. Okay? What we've done is we've chosen two directions to be our coordinate axes in this plane. I could rotate that plane or rotate my coordinate axes in that plane, and those would still be valid vectors. Okay? They would still be valid eigenvectors. In other words, these two eigenvectors, the ones associated with the degenerate eigenvalues, are not unique. So if we used a different routine that had different defaults, we could get different answers. Okay? In fact, let's check and see what eig does instead of eigh. Okay? It turns out that it does return the same eigenvalues, of course, but now it's complex, and it must do that. And it also does return the same eigenvalues, eigenvectors. Okay, again with a sign difference or sign differences. Okay, but it didn't have to. Okay, in fact, we can verify that that's true by, let me make a copy of B. So this will be my alternative B, and let's define this by just taking linear combinations. And I was playing around, so let's do this. Let's do this. Okay, so let's just take linear combinations of the original two vectors. So this is the first vector, and this is the second vector associated with the eigenvalue 1. So let's sum them, and we want to normalize it, so we divide by the square root of 2. So this is like v1 plus v2 divided by the square root of 2. And let's let the other one be the orthogonal version of that. Okay, v1 minus v2 divided by the square root of 2. So my alternative matrix is this. Okay, notice that looks different than the original. The last column is the same, but what I've done is I've taken different linear combinations of these two so that these are still orthogonal. This is still an orthogonal matrix. This is still a matrix that diagonalizes our original matrix. We can verify that by seeing that this is still orthogonal. The transpose is still the inverse. And we can verify that if we use this alternative matrix, this still has diagonalized A. The eigenvalues are still along the diagonal. So again, this is a long way of saying that these vectors for degenerate eigenvalues are not unique. Okay, they're only defined up to rotations, inside this the subspace that defines them, or if you like, orthogonal linear combinations. Okay, and so depending on the routines you use, you can get different answers, and it's still all perfectly valid, and we know how to check that. Okay, so again, we verified that it has all the appropriate properties. Okay, with that, we can now go ahead and solve lots of interesting physics problems that involve eigenvalues and eigenvectors, and of course we get to do some of that in the homework, in the lab, and hopefully we'll have some time to do a little bit of that in class on Wednesday.